Hello, I am Sreshtita, third year ECE section B, roll number 620253. In this video, I am going to explain you about simplex algorithm in linear programming along with the Python code. Linear programming is a mathematical optimization technique that is used to maximize or minimize a linear objective function subject to linear equality or inequality constraints. What are constraints are? Constraints define a feasible region, which is the set of all possible values of the decision variables that satisfy the constraints. So what decision variables are? These represent the quantities that need to be determined, and the objective function represents the measure of performance that needs to be optimized. So in linear programming, simplex algorithm is widely used method to solve the linear programming problems. Simplex algorithm is an iterative algorithm that systematically moves from one feasible solution to another, improving the objective function value with each step until the optimal solution is reached. The simplex algorithm works by starting with an initial feasible solution and iteratively improving it by moving from one feasible solution to another, with each step improving the value of the objective function. Steps involved in simplex algorithm are: first, converting the linear programming problem into standard form by introducing slack variables and forming the initial feasible solution. And then we determine the objective function value at the initial feasible solution. Select a non-basic variable to enter the basis. Determine a variable that will leave the basis. And update the basis by replacing the leaving variable with the entering variable. And recalculating the value of basic variables and objective function at the new feasible solution. And repeating this step until we reach the optimal solution. So let's see this with an example. So here our example is maximizing the value z, which is 3x1 plus 2x2, subject to the constraints x1 plus 2x2 less than or equal to 4 and x1 minus x2 less than or equal to 1, where x1 and x2 are greater than or equal to 0. So this we can start by converting the problem into standard form by introducing the slack variables. The slack variables s1 and s2. And here we do slack variables should not affect the objective function. So here we take the coefficients of slack variables 0 so that it won't affect the objective function. So here we take the update the objective function as 3x1 plus 2x2 plus 0s1 plus 0s2, and we are updating the subject constraints, introducing the slack variable s1 in the first equation and s2 in the second equation. And here s1 and s2 should be greater than or equal to 0, which means when we introduce the s1 and s2 which are greater than 0, it means x1 and x1 plus 2x2 is obviously less than or equal to 4 and x1 minus x2 is obviously less than 1. So now we can form the initial feasible solution by setting the slack variables to the respective constraints and non-basic variables to 0, which is s1 is equal to 4 minus x1 minus 2x2 and s2 is equal to 1 minus x1 plus x2. And at this value, the initial feasible solution is z is equal to 3x1 plus 2x2. Next, we select a non-basic variable to enter the basis. We'll choose so here we will choose x1 since it has the highest positive coefficient in the objective function, and it is not to determine the variable that will leave the basis. We'll calculate the ratio of constant term to the coefficient for each variable in the column of x1. For equation 1, 4 by 1 is 4. For equation 2, 1 by 1 is 1. Since the equation 2 has smaller ratio, s2 will leave the basis, and we update basis by replacing s2 with x1. So now x1 is equal to 1 minus x2 plus x2, and s1 is 4 minus x1. So instead of x1 we take x1 minus 2x2, and here we take x1 as 1 minus s2 plus x2, and which gives us the solution 3 plus s2 minus 3x2. And at this solution, at this value, the objective function value is 3 minus 3s2 plus 5x2. We will choose x2 as non-basic variable to enter the basis since it has the highest positive coefficient in the objective function. It is not currently the basis now. And to select the variable which is leaving, we do the ratio again, 1 by minus 1 and 3 by 3. Here we only take the possible number ratios. So equation 4 has a smaller ratio which is positive. So s1 will leave the basis, and we update the basis by replacing s1 with x2. And so yeah, we do the ratios again and repeat the same value, and we substitute them in the objective function, and we get the value 8 minus 5s1 by 3 minus 4s2 by 3. Here all the coefficients of the objective functions are negative. Therefore the current optimal solution is x1 is equal to 2 and x2 is equal to Now we'll take another problem and solve it using Python. Here the problem statement is, suppose there are 5 potential locations for a new antenna numbered 1 to 5. The cost and benefits associated with each are shown in the table. Next slide. So for the budget of $40,000 for the installation of antenna, ensure that the antenna's coverage area overlaps with at least 200 square kilometers and the signal strength is at least 70. So yeah, this is the table and these are the benefits associated, and they ask the least signal strength should be 70, and here everything is 70 and above, so we can consider all the antennas here. So now we will convert this into a linear programming problem. So first we'll choose the decision variables and we'll take as x1, x2, x3, x4 and x5 as the decision variables indicating whether to install or not the antenna, and here we take them in binary values, which is 1 means we can install the antenna, 0 is we are not installing the antenna there. So yeah, object function is to maximize the coverage area while minimizing the cost, which can be expressed as maximizing 100x1 plus 120x2 plus 80x3 plus 150x4 plus 90x5. We have to maximize this value. We are subjecting this to the constraints, budget constraint and coverage area constraint. So budget constraint is 10,000 x1 plus 1 12,000 x2 plus 8,000 x3 plus 15,000 x4 plus 9,000 x5 should be less than or equal to 40,000, and the coverage area constraint 100 x1 plus 120 x2 plus 80 x3 plus 150 x4 plus 90 x5 should be greater than or equal to 200. Here x1, x2, x3, x4, x5 are the binary variables. Now code. We are writing the code using the pulp library. So now first what we have to do is import the pulp library, and then we define the problem as a maximization problem, saying taking problem is equal to pulp.lp problem. LP problem is linear programming problem, and we are naming this problem as antenna position optimization, and we are using, since we are taking this as maximization problem, we use pulp.lp maximize, and then we define the decision variables as binary variables, which is pulp.lp variable and category binary, and now we define the objective function and the constraints. So we update the problem with these equations. So problem plus equal to the objective function and problem plus equal to the constraints, and then we solve the problem with the pulp solver, which is problem dot solve. So now we solve the problem. Now we have to print the solution. So for printing a solution, we use print optimal solution, and then for variable in problem dot variable, print f variable is equal to variable value. So value is a binary, we know 1 or 0. So but if it is showing 1, it means we are installing an antenna. If it is 0, we are not installing an antenna. And then the next step is for knowing the coverage area. For maximum coverage area, we take all the sum, and this is the output after running that code, which is x1, x2, x3 and x5 is 1 and x4 is 0, which means we are installing antennas at 1, 2, 3 and 5 together, and we'll get the total budget as $37, which is less than 40,000, and the maximum coverage area is 390 square kilometers, which is greater than 200 square kilometers. So this is our optimal solution for this problem. We can change some values of the coverage constraints or budget constraints or signal constraint, and we can do this. Thank you.